So let's take a look at what's actually going on when we talk about a reaction taking place. As we just talked about, when we have a reaction, we're going from the reactants to the products. The reactants, have this energy difference between the reactants and the products, and the reactants usually have to gain a certain amount of energy before they progress to the products, and this is what we call our activation enthalpy, or activation energy. And this high energy state is what we call the transition state, or activated complex. It is a temporary metastable state that exists for a fraction of a second before it collapses to the product. If the reactants have enough energy, they're able to get over this potential energy barrier, they're able to proceed. So, but what's going on with these reactions? I mean, how do reactions take place? And so we can start to discuss what's happening with the reactions. We talked about how we have two molecules coming together and they bonk into one another, and in that process, that's where the activated complex forms, and out comes the product. Yay! Alright, everybody's happy. But that would sort of imply that every single chemical reaction would involve two molecules slamming together. And that's not exactly the truth. If two molecules were slamming together, we could look at this from a molecular point of view. If it was just two molecules bashing together, well, that would sort of imply that this would be a sort of second-order kinetics, where compound A and compound B were bashing into each other, and if you increase the concentration of A or increase the concentration of B, you would get a certain rate. So all the reactions would be overall order of 2. But that's, as we know, that's definitely not the case. So for this, we have to bring in this idea of the mechanism and the related elementary steps. Now, the mechanism is the overall process that takes place. It is simple sub-reactions that combine together to form the product that we're interested in. And each of these simple sub-reactions are what we call elementary steps. They are simple interpretation of what's going on at the molecular level. So let's take a look at it. Let's take a look at an example where we can illustrate this. Let's take a look at the decomposition of N2O. N2O can be decomposed into N2 and O2. 2N2O produce N2 and O2. That's the overall chemical reaction. And like what we did with thermodynamics, we can build up reactions that make this more complex reaction. What do I mean by that? 2N2O going together to produce N2 plus O2. Now, at its simplest level, we can think of this as one of two different ways of this behaving. We can think of it as, if you actually draw the Lewis dot structure of N2O, what you see is N2O is a linear molecule. We can imagine two of these N2O structures coming together. And again, this is our simplistic bashing together model. Bash. and falling apart to produce O2 and N2. This would represent an elementary step. Two of these molecules coming together and reacting. Now, even though I've been harping on this continuously since day one when we're talking about kinetics, where we don't use the stoichiometry to predict the rate law, we can build a rate law associated with this. If we have two molecules coming together, we could imagine the rate of that reaction equal to K times N2O, N2O, or the rate being equal to K times N2O squared. So that would be a preliminary rate law for this simple elementary step. But there's another way of looking at this reaction. Rather than imagining it as two N2O molecules coming together, why can't we imagine it as this NO molecule falling apart to produce N2 plus oxygen? We can imagine conceptually just breaking that bond and doing a little bit of rearrangement of electrons and forming this oxygen atom. And then that oxygen atom, so this would be one step. And then that oxygen atom could then combine with a second N2O to produce O2 and another N2, where it bumps up into this, bumps up against this oxygen, bumps up against that oxygen, and that nitrogen spitting it out. And this would be the second step. Now, this is something we imagine. This is where we use our chemical intuition and our knowledge of what goes on at the molecular level, strong bonds, weak bonds, to build a picture for what might be going on. Now, notice, if you combine these two reactions, we have some species in there, like this oxygen, that aren't present in the starting materials or the reactants. These are what we call intermediates. So this is an intermediate. Now the intermediates are generated by the reaction, and then they're consumed by the reaction. And if you add these two reactions together, you get N2O plus oxygen plus N2O goes to N2 plus oxygen atom plus O2 plus N2. And what we see is that the oxygens cancel, leaving us with the following balanced chemical reaction. Now, the question we have to ask ourselves is, which of these is the correct one? So, what we can turn to is what we call the molecularity. We can sort of classify these reactions based upon their molecularity. And that is how many molecules are involved in the elementary step. So again, we've looked at this first example. This is where we have two molecules interacting. This would be a bimolecular. Whereas in this example, this lower example, this would represent a unimolecular reaction, because it only interacts with one other molecule. And this would be a bimolecular. There are also termolecular reactions. They don't have to be the same compound. They can be two separate compounds and they come together. And the bimolecular and unimolecular reactions can tell us information about the rate. A unimolecular reaction should have a rate law that would look like our molecularity of 1. Things that we've seen already. Our first order rate law. Bimoleculars are all second order. Termoleculars are all third order. Now, for us, how do we figure out which it is? Well, we can do some sort of chemical tests. We can look at it. But oftentimes there's in multi-step systems, well, first of all, if it was second order, we could use the rates. What we would have to do is we turn to the rate of the reaction. The rate of the reaction will reflect the molecularity. And what it's funny is it's the most sensitive to the slowest step. We can tell what the slowest step is by looking at the rate law. Now, if we were to measure this, I mean, we can sort of imagine what the rate law for each of these is. This would be, the rate would be equal to K N2O. This one, the rate would be equal to K N2O as well. Though technically the oxygen would be all involved in the process. But we might not see the oxygen in the reaction. So how do we observe it? It may not be present or present in such small amounts that it's not visible. We can turn to then what we call the rate limiting step. Which is the slowest step in the reaction. Slowest elementary step in the reaction. And this would allow us to, the rate law will reflect the rate limiting step. So we take a look at an example from our textbook. So we look on 588. They show the reaction of 2NO plus O2 going to 2NO2s. Now, termolecular reactions are quite rare, where 3 atoms come slamming together at the same time. But we can also imagine this in terms of oxygens reacting with nitrogens to form like a nitric oxide. We can envision a nitric oxide reacting with an oxygen to produce NO2 plus oxygen, and then that oxygen bonding with another nitric oxide to form another NO2. Pretty much very similar to our last example. This is step 1 and step 2. And there would be some sort of rate law associated with this. K would be equal to the reaction of NO and O2. So that would be the rate associated with, the rate law associated with that particular generic reaction. We could also write a generic rate law for the second one, which is also a bimolecular reaction, but again we would we wouldn't actually see the O being formed, so it would just be K versus O. And with this oxygen being unobserved in the reaction. And so when we measure the rate of these, we would find which one would actually progress. Or we could imagine a different route, where instead of the two NOs playing a role, we have an NO binding to another NO to make N2O4. This would be, the rate would be equal to K NO squared. And then that N2O4, that intermediate bonding to another oxygen to split off and form our two NO2s. The rate would be first order with respect to oxygen, with the N2O4 being a sort of hidden intermediate, which we wouldn't see. Now, if we actually measure the rate of this reaction, what we see is the rate law of this reaction. We see that the rate of this reaction is actually KNO2. This is actually the rate law, experimentally determined rate law. Even though oxygen is part of the stoichiometry, doesn't play a direct role in the overall rate. And so we know that this is the slowest step, and it's the only potential step in the mechanism that is in agreement with what we observe in the products. Now, how do catalysts affect these materials? Well, catalysts do a number of different things. The way catalysts do, one of the things, catalysts speed up the reaction. Another way of thinking about that is the catalysts alter the rate constant. And the way they do this is by fundamentally altering the activation energy. Reactants going to products, activation energy. What a catalyst does is it lowers that activation energy. And there are many ways it does this. One of the easiest ways to think about them is it introduces strain in the molecule, enhancing the reactivity, or it brings the compounds together, forcing them to react more readily. Catalysts show up in our rate laws. Rate law, they're proportional, they usually play a role in the rate law. But they aren't consumed in the reaction. They're usually regenerated in the reaction during the process. And so what this does is it lowers the activation energy, speeds up the reaction.